Have you ever stopped to think about how a simple touch or a smell can suddenly spark a thought or a long-lost memory? It feels instant, right? Well, today we're going to trace the incredible high-speed journey of a single electrical signal as it zips through your nervous system. We're going from a simple trigger to a complex message, all in a fraction of a second.
So, let's ask the big question right up front. How does a single thought actually travel through your brain? I promise you, it's not magic. It's this beautiful, perfectly timed dance of electricity and chemistry, and we are going to break it all down, step by fascinating step.
Get ready, because we're about to go on a high-speed chase, but on a microscopic scale. This is a journey that's happening billions, literally billions of times every single second inside your head. So, okay, let's dive right in.
Every great story needs a hero, and the protagonist of our story is the neuron. These incredible, specialized cells are the basic building blocks of your entire nervous system. They're the messengers, the carriers of information for everything you think, feel, and do.
And if you look at a neuron, its structure is just perfectly designed for this job. You've got the dendrites, which are like these little antennas, constantly listening for signals. All those signals get funneled to the soma, the cell body, which acts like a central processor. If the incoming messages add up to something important, bam! The axon, this long cable, transmits the signal away. And finally, at the very end, the synaptic terminals pass that message on to the next cell in line.
But here's the thing. Neurons are not solo acts. They have a whole support crew working behind the scenes called glial cells. Now, these aren't just filler. They're absolutely essential. They bring nutrients, they clean up waste, and as we're about to see, they play a superstar role in making sure our signal travels at incredible speeds.
So, when a neuron is at rest, it's not actually resting at all. It's busy, actively maintaining a state of electrical tension across its membrane. The best way to think about it is like a coiled spring or a drawn bow, just storing up all this potential energy, ready to snap into action at a moment's notice. And this is how it creates that tension. Just look at the difference in these numbers. We're talking about charged particles, or ions. Inside the cell, you've got a ton of potassium. Outside the cell, a ton of sodium. Your neuron actually burns a lot of energy just to keep this imbalance going. It's like constantly pumping water uphill.
So what does this all mean? Well, this separation of ions creates what we call an electrochemical gradient. With all that potassium and some negatively charged proteins stuck inside, the inside of the neuron ends up with an overall negative charge compared to the outside. That separation of charge is the stored energy. It's the coiled spring.
And that stored energy even has a specific value. We call it the resting membrane potential, and it sits at about -70 millivolts. That's its baseline. It's primed. It's ready, just waiting for the trigger.
And when that trigger comes, that's when we get the main event, the action potential. This is it. This is the nerve impulse itself. It's a rapid, dramatic, all-or-nothing explosion of electrical activity that shoots down the axon. Okay, let's break down this wave. First, some incoming signal makes the inside a little less negative. If it hits a critical point, the threshold, specialized sodium gates fly open. Sodium ions, which have been crowded outside, come rushing in, and for a split second, the inside of the cell becomes positive. Then, just as fast, those sodium gates slam shut and potassium gates open. Now the positive potassium ions rush out, bringing the charge back down to negative before everything resets for the next signal. Now, this is absolutely crucial. The action potential is all or nothing. You can't have a half action potential. It either fires at full strength every single time or it doesn't fire at all. This is what guarantees that the message is sent loud and clear without fading out over long distances. All right, the action potential has been generated. The fuse is lit. Now that signal needs to travel all the way down the axon, which can sometimes be over a meter long. To do that, it has to be incredibly fast.
And remember those glial cells, our neuron support crew? This is their moment to shine. Many axons are wrapped in this fatty layer called a myelin sheath. You can think of it just like the plastic insulation on an electrical wire. It prevents the signal from leaking out and forces it to regenerate at these specific little gaps, letting the signal basically jump from one gap to the next. It's a huge shortcut.
And the effect this myelin has on speed is just staggering. Look at this. An axon with no myelin might send its signal at, say, 2 meters per second. But a myelinated one, they can hit up to 120 meters per second. That's over 260 miles an hour. That's the difference good insulation makes.
So our signal has raced down the axon at top speed and made it to the end. But now it faces its final challenge, a tiny physical gap called the synaptic cleft. The electrical signal can't just jump across this gap, it has to find another way. So to cross this divide, the signal has to do a quick change act. It converts from an electrical signal into a chemical one. The arrival of the action potential triggers the release of these little chemical messengers called neurotransmitters. They float across the tiny gap, bind to receptors on the next neuron, and boom, the message is converted right back into an electrical one.
And this whole release process isn't just random, it's a marvel of molecular engineering. You've got this whole team of specialized proteins working together like a tiny complex machine, making sure those neurotransmitters are released at the exact right moment. It's unbelievably precise and fast.
So the chemical message has crossed the gap and been delivered. But what happens now? Does the next neuron fire off its own signal and keep the chain going? Or does the message just stop right here?
Well, it really depends on the message that was sent. Some signals are go signals. They're excitatory. They make the next neuron a little less negative, nudging it closer to its own firing threshold. But other signals are stop signals. They're inhibitory. They actually make the neuron more negative, pushing it further away from the threshold and making it less likely to fire.
And here's the amazing part. A single neuron is getting thousands of these go and stop signals all at once from all different neurons. It's constantly doing a kind of math, adding up all the goes and subtracting all the stops. And only if the go signals win by enough of a margin will that neuron reach its threshold and fire its own action potential. It's basically a tiny biological computer making a decision. We've just followed the incredible journey of one single signal, from a tiny whisper at the dendrites to a shout across the synapse. Now imagine that process, but happening trillions of times every second, creating this impossibly complex symphony of communication inside your brain. That symphony is what gives rise to every thought, every feeling, and every action you'll ever have. It's the very foundation of who we are.